In the last class, we have discussed about the current components in a transistor. So look at the transistor once again. This is a PNP transistor, and when it is biased by the forward bias in the emitter base junction and the collector to base junction is reverse biased by a relatively larger potential, an emitter current is set up. Almost about 98% of this emitter current goes to the collector in this direction, the positive current. Since the notation we follow normally is as shown here, like the current entering the node is denoted by a symbol IC. The actual current is flowing in this direction. As a result, IC is going to be negative. Therefore, IC is equal to minus alpha IC. Alpha is of the order of 98 or 99%, and or 0.98 or 0.99 plus IC naught. IC naught is the reverse junction current. Okay, and in this particular case, IC naught is negative. Actually, the current flows from the base region into the collector, and this current is IC naught is negative. Therefore, it is about 0.99 IC. I'm sorry, IE. It's a mistake here. It is IE, and with some negative current. Overall, it's the currents get added, and both are positive components. If you are considering the current in this direction going out of the collector terminal, that current is a positive quantity plus another positive quantity. Okay, because of the notation, you have the sign coming here as negative, and this is also negative. Actually, IC naught itself is negative, IE is positive. Therefore, so this is some negative quantity and another negative quantity. It is a larger negative quantity than any one of these, and that negative quantity is for this IC going in. For the IC that is coming out, if you change the notation as IC coming out of the terminal, then it will be a positive expression. It is going to be plus alpha IE minus IC naught. IE is positive because actual current direction is also into the terminal. IE is positive. Therefore, alpha IE is going to be a positive quantity, and IC naught is negative, the reverse saturation current. Therefore, minus IC naught will become now plus IC naught when you denote the current as going out of the terminal. Please note that the only difference here is the notation, nothing else. If you have any difficulty in denoting the current this way, you may change the notation as the current going out, IC as the current going out, and have an expression plus alpha IE minus IC naught. For that IC going out of the collector terminal. Now, let us discuss about the common base configuration. Common base configuration. As I explained previously, there are three different combinations of input outputs that are possible, because you have three different terminals over here. I mean, three different combinations with meaningful representation possible. One of them is the common base configuration. In fact, the circuit biasing arrangement, the voltage that is to be applied to make this junction forward biased and this junction reverse biased is with a common base configuration here. Okay, here. So now in common base configuration, base is made to be common to input and output. And here input and output means not for biasing voltages, but when you talk about amplifying signals by applying some speed signal or some time varying signal at the input, and on the output you expect an amplified signal to be obtained. Okay, so in terms of that, with the common base configuration, you apply an input signal over here between emitter and base, and you take the output signal by connecting a resistance over here. We take the output voltage across the resistance. Therefore, the emitter and base forms the input side and collector and base forms the output side in the case of a common base configuration, which is known as CB configuration. When you form an amplifier with this kind of input and output arrangement, so you get some kind of amplifier with certain characteristics, like a high voltage gain amplification and low input resistance. Similar to this, you have different kinds of characteristics of the amplifier that comes into picture. Okay. So hence in this case, the emitter to base junction is the input junction and the collector to base junction is the output junction. Now let us look at the characteristics of the amplifier. So if you look at the input characteristics here, between the emitter and base, it is a PN junction. Is this PN junction totally, it's a PN junction, is it totally independent of this collector to base junction? Not really. There is some effect by the voltage of the collector to base junction, because if the potential across the collector to base is high, whatever is the current that flows inside is attracted or is drifted downwards, the potential difference between the base and collector, and that is accelerated to the collector, the current is. If the potential is small, that acceleration for the injected carriers, injected holes into the P region, are accelerated to a lesser extent if the collector to base junction potential is small. So because of this effect, this PN junction characteristics between emitter and base vary slightly. So with this variation, the PN junction characteristics can be given like this. Input current is the emitter current. It is usually expressed in milliamperes, and the base to emitter potential VBE expressed as volts. As you know, it is like a PN junction characteristics like this. Say the collector to base potential is 20 volts, the characteristics would be like this. And if the collector to base potential is slightly reduced to 10 volts, this PN junction characteristics changes to some extent in this fashion. VCB is equal to 10 volts. And if the voltage is further reduced, the characteristics would change to, so this kind of characteristics. This is VCB is equal to, say, 1 volt. An interesting case is when the base, the collector junction is totally open. If the collector is open, it acts like only a PN junction, and the characteristics would be like that of a PN junction diode. In which case, so the slope will further go down. With open collector, the slope will further go down, and it is exactly equal to that of a PN junction diode. Okay. So what is responsible for the current to increase with a higher slope when VCB is high? That is the drift or the attraction by the base to collector junction potential. That potential is, there is a potential gradient, high potential gradient, because of which the injected holes by diffusion, the diffused holes into the base are attracted or dragged into the collector with some drift or with some attractive force. Because of this reason, there is a tendency in increasing the emitter current with a slight increase in the base potential. That's why the characteristics shift inwards. Okay, so this is the input output characteristics with the cut-in voltage roughly around placed roughly around 0.5 volts, and this is about 0.6 and 0.7, similar to that of the diode, except for this minor difference. Okay, so this is the input characteristics of a typical common base configuration amplifier and common base configuration. Now let us look at the output characteristics. With the input, so that means to obtain the characteristics of the output characteristics, what do we do? When you apply some input current, okay, and with that particular input current, how does the volt ampere characteristics behave? So that's what is given by the output characteristics. Well, if there is 1 milliampere current, how much of collector current do you expect? Almost. So 1 milliampere of collector current is expected, irrespective of the collector to base potential, once it is reverse biased, of course. And when this current is say 10 milliamperes, how much is the collector current? Collector current would be 10 milliamperes, irrespective of the collector to base junction potential. So because of this reason, the output characteristics is flat as shown here. IC, with IC given as the current going in, so naturally the actual IC is with opposite sign, therefore the current would be say -1 or -2, -3, -4 and -5 milliamperes, given that IE is also 1, 2, 3, 4, 5 milliamperes, with the collector to base junction potential represented in the x-axis. This is in volts. Say 0, this is 5, 10 volts, 15 volts, and so on. Irrespective of the collector to base junction potential, the current IC is going to be alpha IE, which is approximately equal to IE, and it remains constant with changing potential. Okay, therefore the output characteristics is like this. It is interesting to see what happens when the collector to base junction is slightly forward biased. So going back to this, the collector to base junction, even when the collector to base potential is 0, okay, because of the space charge region, you have some potential gradient, and that is good enough to almost drag the draw the almost the full collector emitter current into the collector. But when this is forward biased, so this one also acts like another PN junction, with the P applied to a positive potential compared to the N side. So then these two behave like two independent PN junctions, in which case there would be current flowing into the emitter, there would be current flowing into the collector, and both the currents put together go out of the base and complete the circuit. Because this is a PN junction diode, and the circuit looks like this. So there would be current flowing in here, and there will be current flowing in here, and that will be coming out. So the IC is equal to alpha IE minus alpha I is no longer valid. Okay, therefore in fact IC becomes now positive from negative. Therefore, the characteristics IC drops so very rapidly with small amount of positive potential. So this is, if this is minus 1 volt, with a few millivolts, few tens of millivolts itself, the collector current drops because of the disappearance of the potential gradient. And if you further increase, IC becomes positive. IC becomes positive because both the collector junction and emitter junctions act like two PN junctions, and one loses the control over the other. Hence the characteristics is like this. Now it is interesting to see what happens when IE is 0. What happens when IE is 0? When IE is 0, that means the emitter side is open circuited. How do you make IE equal to 0? When you open circuit the emitter side, what happens to this? So this is equal to a reverse biased PN junction. Reverse biased PN junction. Therefore, you expect some current to flow in this direction, in the PN junction over here. And this reverse current is, as you know, due to the minority carriers, and it is very small, which is of the order of nanoamperes in the case of a silicon diode, and it is of the order of a microampere in the case of a germanium diode. Therefore, we expect a very small amount of collector current to flow. This is just reverse biased PN junction. In the reverse bias in the PN junction, you have the characteristics like this, and the reverse bias, under reverse bias, it has a small characteristics which saturates for a small voltage itself. So that characteristics is this. Okay. So in which case IC is equal to ICO itself, and this ICO is naturally negative for the convention which we are following, and it is of the order of, I repeat, it is of the order of 1 nanoampere in the case of a silicon transistor, and is of the order of a microampere in the case of a germanium transistor. This current is also known as ICBO. It is the current, collector current, which flows through the base with the emitter open circuited. So ICBO is equal to IC naught. What is ICBO? ICBO is the collector current when the emitter is open circuited, and that is in this particular case naturally equal to IC naught of the PN junction. Now let us see what kind of how the common base configuration, a circuit in the common base configuration, can act like an amplifier. In earlier classes, I discussed about how a transistor, briefly discussed about how a transistor works like an amplifier. Please look at the circuit diagram. After providing the biasing through two different voltage sources, or maybe even it is possible to also provide forward bias here and reverse bias here using a single voltage source also. Okay. Anyway, so after providing the bias for forward biasing and reverse biasing the transistor junctions. If you apply a small input voltage here and use a resistance, a load resistance here, across the load resistance we expect a large voltage to appear. How is it possible? With the emitter to base junction characteristics, if you look at the emitter to base, please note that for the input signal, when a small voltage signal is applied, you expect a small AC variation in the emitter current. Say here initially, say it is biased to about 0.65 volts here. Now the AC voltage you are applying between the base and emitter may change the potential by plus or minus say 10 millivolts. So 0.65 minus 10 millivolts and 0.65 plus 10 millivolts. So that is the variation. So with this voltage variation in the base to emitter, you get a corresponding current variation in the emitter current. Say at 0.65, say it provides you 6.5 milliamperes of current, and with 10 millivolts negative it would be 0.64. With 0.64 volts, say you will get 6.4 milliamperes, and 0.65 plus 10 millivolts, when the AC signal is positive, it will go to about 0.66 volts, and see collector emitter current is say 6.6 milliamperes. This is a typical example I am taking. Say the voltage variation corresponds to a current variation like this, assuming that the slope of the characteristics is 10 ohms, and please note that it is almost straight line. So if there is a sinusoidal voltage applied here, you will get a sinusoidal variation in the emitter current. Okay, and if the slope is 10 ohms, so plus or minus 10 millivolts of signal will provide you about 0.1 milliamperes of current variation. Now with this kind of alternating potential, actual IE is going to be the constant IE 0.65 milliamperes plus some alternating IE, and that alternating component will go up to plus 0.1 milliampere and minus 0.1 milliampere above 0.65. This is 0.65, and this is, as I said, sometimes plus or minus 0.1 milliampere. I'm sorry, this is 6.5 plus or minus 0.1 milliampere. Strictly speaking, if it is a sinusoidal voltage, 6.5 constant plus or minus a 0.1 into some sin omega naught t. So that is the total emitter current that is going to take place. Are you interested in the DC component or the AC component when you talk about the amplification? It's naturally the AC component. So we are interested in this portion. This is anyway there. Okay. So if this is the AC component in the emitter current here, due to the application of this voltage, now what is going to be the corresponding collector current variation? Similarly, you have in the collector current, you have IC plus some small IC, the collector current variation. And what is this IC going to be now? So that is, since IC is about alpha time, IC is alpha times IE with a very good approximation, alpha times IE. So this IC is going to be this IE multiplied by alpha. So approximately the same kind of variation appears in the collector side also. Now if the resistance is say 1 kilo ohms, and if the collector current variation is, say let me use the same term, if the resistance is 1 kilo ohms and the collector current variation is about plus or minus 0.1 milliamperes, or if it is a sinusoid, plus or minus 0.1 sin omega naught t. I am only talking about the alternating component, and when this drops across this, it will give you a voltage which is equal to 0.1 volts. And if this resistance is 10 kilo ohms, 10 kilo ohms into 0.1 sin omega naught t will give you a voltage of 1 sin omega naught t. So for 10 millivolts of input signal, plus or minus 10 millivolts of input signal is becoming plus or minus 1 volt, and the amplification factor or gain is equal to 100 in this case. But the input signal is a 10 millivolt peak sinusoidal signal, output is going to be a 1 volt peak sinusoidal signal. Therefore, the amplification or the gain in this particular case is equal to 1 volt divided by 10 millivolts is equal to 100. So how are you getting this? So input voltage Vi is equal to 10 sin omega naught t in millivolts. So output V naught, well, this is giving rise to an input current which is equal to 10 sin V omega naught t divided by the slope of the curve, input characteristics. So if we call it as Ri, so that divided by Ri is the input current variation, and if Ri is of the order of 10 ohms, then it is going to be 1 sin omega naught t. If Ri is of the order of 100 ohms, in this particular case I have taken it as 100 ohms. If it is 100 ohms, it is going to be 0.1 sin omega naught t millivolts when Ri is 100 ohms. If Ri is 10 ohms, please note that it is 1 sin omega naught t. The variation is 1 milliampere. However, with Ri is equal to 100, it is 0.1 milliamperes peak. Now, IC, the AC component of the IC is alpha times, this is IE, I have to write it as IE, alpha times IE. So that is approximately equal to 0.1 sin omega naught t milliamperes. Now, the output voltage V naught is equal to IC into RL, and if RL is 10 ohms, so then this is going to be 1 into sin omega naught t. So it's volts. Therefore, the gain is the output voltage divided by the input voltage is equal to 1 by, so 1 volt by 10 millivolts. Peak to peak difference is the ratio is the AC signal ratio, so that is equal to 100. Here I would like to mention one thing. The output current is, please note that the IC is going to be alpha IE, and it is going to be constant, almost constant, irrespective of variations in VCB. When you incorporate a resistance over here between the collector and the base, the effective VCB is going to be varying, because this is this constant potential plus this variation across the load resistance, these put together. So this VCB is going to change, and with VCB changing, is IC going to change? Practically no. Therefore, I can apply RL into IC as the output voltage, because IC is only going to be guided by IE and not by VCB. Hence, this can be applied. If you look at the output side characteristics, please note that the output side current is constant with respect to variations of VCB, and if you take the slope is going to be 0. So this is also like a resistance, output resistance, with the voltage and the input current. With alternating voltage applied, does the input current change? The collector current change? If I vary VCB from 5 to 15, do you expect any collector current to change? Collector current is going to remain constant irrespective of variation in the voltage, and that is almost 0. When do you expect a current to be 0 with varying voltage applied? When the resistance is infinite. Hence, the output side, if you view this characteristics as the device has an output side resistance, in the output side it acts like a resistance, because when you apply a voltage here, you expect some current variation, some current. When you apply an alternating voltage here, you expect an alternating current to flow when the input side is left open. But here what's happening is it is acting like a high resistance, particularly because of its reverse junction. And on the other hand, on the input side, we have seen that by changing the potential slightly, we expect a large variation in the input current. Therefore, the resistance here is low. So effectively what this transistor is doing is, it is transferring a low resistance input to a high resistance output. Therefore, a transistor is a trans resistor. Hence, it is known as a transistor. Okay. So this transistor action, how is this amplification possible? It is because a small voltage is producing a large current, and that current is getting transferred to the output, and when you pass it through a resistance, you are getting a large voltage, and that large voltage is not disturbing this IE to IC relationship. If it is disturbing the IC to IE relationship, you won't get this kind of amplification. So because of this transfer resistor action, this amplification has been possible. If this 10 millivolts causes about, say, 0.1 milliampere current variation, and that 0.1 milliampere current becomes again say some 0.1 microampere current variation here, and we pass it through a 1 kilo ohm resistance, you won't get any amplification. Okay, so it is because this variation is not disturbed, this has been possible. This is actually, I have not put the title, but please note that this is how a transistor acts like an amplifier. This is the title. And similar to this, you have a different configuration, which is very important. It is known as common emitter configuration. Now in this configuration, the emitter is common to the input and output. So use the same PNP transistor, and you apply a signal to the base. First of all, you bias it. And apply an input signal over here, and use a large resistance RL, and tap the output voltage over here. So this configuration is known as common emitter configuration. Here emitter is common to the input side and emitter is common to the output side. Okay, so the input is applied between the base and the emitter, and there is a small mistake over here. So this is the circuit, and the output is tapped between the collector and emitter. Now what is the input current over here? The input current in this particular case is the base current. The output current in this particular case is the collector current. Hence, the input output characteristics, the input side characteristics is the characteristics between the base current and the base to emitter potential. So this is in volts and this is in milliamperes or microamperes. In the earlier example, the input current is the emitter current and now it is the base current. What is the ratio between the emitter current and base current? Please note that we said when there is an emitter current, about 98 or 99% passes to the collector and only 1% or 2% goes to the base. Therefore, the base current is about 1/100 or 1/50th of the emitter current. So here in the previous configuration, we talked of currents which are of the order of a few milliamperes, say 10 milliamperes and 20 milliamperes. Now, for the same kind of operating emitter current, the currents for the base in this configuration would be 1/100th or 1/50th of this. Therefore, we talk in terms of say 10 microamperes, 20 microamperes, and so on. And the characteristics is between the emitter and base. The voltage current characteristics remains almost the same as that of the previous case, except for now it is plotted against IB, not IE. IB to IE ratio is anyway almost constant. So with VCB equal to 20 volts, the characteristics would be like this, and equal to 10 volts as I have drawn in the previous case. So with 10 volts it would be like this, and with say 1 volt it would be like this. That is in terms of VCB. Now what is important here? Do we talk in terms of VCB? We'll talk in terms of VCE because the emitter is common between output and input. Therefore, what the same curves appear here for VCE. Now if VCB is 20 volts, VCB is 20 volts, what about VCE? VCE is going to be VCB plus VBE, and VBE is of the order of 0.7 volts or 0.6 volts. Therefore, the same curve which was valid for VCB equal to 20 volts will be valid for VCE is equal to 20.7 volts. And the same curve which was valid for VCB equal to 10 volts is valid for 10.7 volts. With 0.7 volts variation, they do not differ much. Therefore, I'll retain the same characteristics for VC equal 20 volts and 10 volts and 1 volt. It's clear? So that is it. So this is the input output characteristics. Now please note that with 10 millivolts of signal here, the current variation was of the order of 1 milliampere or 0.1 milliampere in the case of the CE configuration. Now it is going to be of the order of microamperes, few tens of microamperes. Therefore, in this case, the slope is going to be higher than that of the common base configuration. What is the ratio? So ratio is going to be, so that 1 by 50th or 1 by 100. So this resistance is going to be 100 times or 50 times more than the resistance in the case of common base configuration. Here itself is a characteristic difference. In common base configuration, you have a low input resistance, and in common emitter configuration, you have a high input resistance, because few millivolts of variation will give you a few micro amperes of, or few tens of microamperes of variation in the current. So let us look at the output characteristics. In the output characteristics also, a similar difference is applicable. The difference is, now instead of VCB, now we will plot it against VCE, and the current is IC. And the difference is, between VCB and VCE, the difference is VBE. Hence, the characteristic shift rightwards to some extent, and the characteristic says something like this. And this is for different, now plotted for different IBs. This is IB, maybe say 0, this is 10 microamperes, 20 microamperes, 30 microamperes, and so on. Okay. And we'll continue this discussion in the next class. Okay.